Welcome to Economics Trainer. This video was made to help you strengthen your skills in microeconomics. Here we have a sample question, care of brighttutoring.ca. It's the kind of question you'd expect to see on a test in a second-year microeconomics class. Let's work through it together. So here's the question. Suppose we have a consumer with a Cobb-Douglas utility function of u equals x to the 0.1 times y to the 0.9, which gives them a marginal utilities of mux equals 0.1 times x to the negative 0.9 times y to the 0.9, and a marginal utility of y equal to 0.9 x to the 0.1 y to the negative 0.1. And the consumer has $100 to spend to purchase goods X and Y. What we have to figure out is the consumer's optimal bundle when the price of X is 2 and the price of Y is 9, and then again when the price of X increases up to 5. Once we have those two questions figured out, we can use that information to solve the last question here to figure out what price would maximize the total revenues or expenditures on X. So let's start off here at the top by finding these optimal bundles. So here's all the information we have. Let's start by drawing out a graph here and saying we have good X and good Y. And then to start, the consumer has $100. So let's draw a budget constraint here. Say, okay, well they have, for a good X, they can have $100 divided by 2 as their maximum value. And then for good Y, the maximum they can buy is 100 divided by 9. So let's see what that. Okay, that's roughly 11. Up here. And then for the second question, you see px increases up to 5. So instead of having 50, we're going to have 100 divided by 5. And this point here, see this is going to move down to 20 for the new budget constraint. And then to find the optimal bundles, we'll say, okay, there's one here, there's one here. We have indifference curves for the first part and the second part. And then we're going to figure out what happens here. Let's label this A for the first question. So let's find this point here. You can see we have tangency between the indifference curves and the budget constraint. So let's start off with the tangency condition. And say, okay, slope in the indifference curve, slope of the budget constraint, the absolute value here. So here we have the marginal utility of x and y. So let's just write the equations on top of each other here. And then for MUY, put its equation on the bottom down here. And on the right-hand side here, we have to use the prices for the original point here. So we'll have px of 2 and py of 9. So working out the algebra here, you can see in the front the coefficients. We have 0.1 over 0.9. Okay, that just becomes 1 over 9. Just keep the 9 here at the bottom. And then for x, we just have to deal with the exponents. So we have negative 0.9 and then minus 0.1. So it'll be a minus 1 in total. So that'll be x on the bottom. And then for y, we have 0.9 minus 0.1. So it'll go positive, and that'll just be y to the 1, or y on the top. And over here, we have 2 over 9. So let's see, okay, we got 9s on both sides. Those will go away. We move the x up, and we get y is 2x. So that's the first equation, which is the tangency condition of part A. And then let's use this with the budget constraint, which is the line we have to be on here. So we say, okay, budget constraint is income equals spending, pxx plus pyy. Let's plug in the numbers here. So we have $100 for income, X costs 2, and Y costs 9. And then what we do here is we combine these two together, and we say, okay, we have 100 equals 2x plus 9, and then where we see y, we plug in the 2x over here, and we solve for x. So let's see here. So we have 2x plus 2 times 9, which is 18, plus 2, that'll be 20x. That's 100. So the optimal bundle at this first point, we'll call it x star A, is going to be 100 divided by 20, which is 5. So that's going to be this point here at 5. We can go over, and we can plug it in, figure out this point for y. You say, okay, if we know x, we know y, you just go back here and say, okay, well, y is just 2 times x, so the y at that point is going to be 10. So that's going to be point A to start here. So that's the first question here. So we have 5, we have 10 for the first optimal bundle. And we just got to do the same thing for the next question, and all we have to do is just change the price of x to 5. So we can do similar work over here for finding this point. If we want to find this point here for point B, we can just do the same work. We say, okay, we'll have the same tangency condition, so most of this work over here will be the same. And we'll say, okay, the left-hand side, nothing changed, so that's going to be y divided by 9x. And then on the right-hand side, we just have to change the prices. So instead of having the old px, we're going to have the new one, which will be 5 over 9. So same thing like before, the 9's cancel, we can move the x over, and we get y equals 5x. That's the first equation, so that's our tangency condition for B. And then we'll take that, and let's plug that into the budget constraint like here. So we say, okay, budget constraint's the same income, so I'll have 100. And that's going to equal the new price of x, which is 5. And then plus 9 for y, and then let's plug in the y here for the 5x. So let's see, we have 100. So we have 5x plus 45x, that's 50x. So the x star B at the second point is going to be 2. So going over to the graph right here, that this point here is going to be 2. And then to go over, see the same point here, we say, okay, let's combine these two together. We say, okay, if we have x, we have y. So the y at this point is going to be 5 times that, so 5 times 2 is 10. Of course, is the same as earlier because its price didn't change. So that's going to be the same point here as the red one. So that's going to be the second question. Let's see here. So here we have 2 and 10. So now that we have these 2 points and we know the demand in both cases, we can use this to figure out the last question in terms of figuring out what would maximize the total revenue and expenditure. So to figure out this last question here, what you have to know is that your total revenue is maximized at a key point. So total revenue is maximized at the elasticity of demand is -1. You have unit elasticity. So that's the key thing. So if we use this identity to figure out the last part of the question here, question 6, we say, okay, for our elasticity equation for demand, we say, okay, let's set it equal to -1. And then let's use the elasticity equation to solve the rest of it. So we say, okay, elasticity is the change in the quantity demanded from the change in price times the price over the quantity. So what we have to do here is we can see the price is what we're trying to solve for, because that's what we're trying to figure out. So see, we have the price up here. That's the variable we're trying to solve. This here we can use to figure out the demand curve. That would convert that to a price. And then this here, you can see here, this is the slope of the regular demand curve. So basically we have to figure out the demand curve here to fill in these pieces. So let's do this over here. So this is where those 2 points from earlier come into play here. And we say, okay, to figure out our demand curve, we can draw it out. So we have x, we have px, and we have our 2 points here. So we say, okay, from earlier when we had a price of 2, you can see the x star A was 5. So it's going to be point A. And then for point B up here, see the xb was 2. And that's for a price of 5. And second point. So if we connect these 2 points, we can figure out our demand curve here. And then use that. So if we assume this is a linear demand, we can go with, okay, we'll say P of x equals mx plus b for the equation of a line. And then we'll use these 2 points up here to figure out the slope. So we know the slope m is a rise over run. So y2, which is our price here, so our second price, 5, divided by the old price, and then over the x2 minus x1, so the x2 is 2, and then minus 5 for the x1. So let's see what we have. 3 over negative 3, and that'll just be negative 1. So we know the slope here is negative 1. And then to find the intercept, we just use one of the points. So we say, okay, one of the points matches the slope. So if we use the original point, 2 and 5 here, we'll say, okay, px is 2. And we know it's now negative 1. The x at that point was 5. And then we can solve for b here. So we have negative 5, move that over, and we'll get b equals 7. So what that gives us now is we can figure out our demand curve here. We say, okay, our demand curve here is going to be px equals 7 minus the xd, for negative 1 for the m. So here, now we have our demand curve. In the inverted form. And we can always flip it around and say, okay, if we move the x to the other side, we'll say, okay, well, we have xd, quantity demanded, equals 7 minus the price. And now we have it in the regular demand instead of the inverted form. And then this is what we're looking for going back here. Because here we have the slope of regular demand, and then the regular demand curve would go in here. So if we look at the slope and say, okay, what's the derivative or the change in xd from here? We'll say, okay, here we have the change in xd from the change in px is negative 1. So if we go back and plug this back in over here, let's see, we have negative 1 equals, well, now that's negative 1 for this part here. And then here we have p, which we're trying to solve for on the top. And on the bottom here, instead of having x, we're going to plug in the equation for the demand curve, which is 7 minus px down here. And what you can see is this whole equation just has the price left over. So what we have to do is just solve for it. So we say, okay, they have -1 on each side. Those two will cancel. And we can move the denominator up and say, okay, we have 7 minus p equals p. And we go over here, okay, let's move the p's all on the right. We get 7 equals 2p. And so what happens here is this p hat, which is the maximum for the total revenue, that's going to equal, let's see, 7 divided by 2. So that'll be 3.5. So if we look over here at this graph here, for this point here, we'll see, okay, here at 3.5, this area here, that box there, which is total revenue, is maximized. So what we have here for this one here, we get 3.5. And that's how you do that question. This video is brought to you by people who like, share, and subscribe to this channel. You can also support my work by buying me a coffee.